Okay, good morning. Let's going on with our unstructured finite volume methods. Let's just remember that the last class we finished our discussion about the cell-centered finite volume method. I would like to also remember that in the cell-centered method, what will be different from what we're going to see today is that in order to find the diffusive terms which involves the gradient in the cell-centered method, we need to have some kind of a graduated reconstruction or calculation of the gradient because it's not readily available for the calculation of the fluxes, diffusive fluxes. Today we are going to start the element-based finite volume method. It is a cell-vertex method. It has some way to construct the control volumes. And what we learned in the beginning, in one of the previous slides, is that the cell-vertex methods, they are methods which the control volume is constructed, is built using the elements. And then here we have a picture showing the grid, which is the elements, one of the elements, and then the control volume here, which was constructed with parts of the elements. So this element, which is a quadrangular element, is divided in 4 sub-control volumes or sub-elements, and one of them enters in the flux calculation for this control volume, where the variable is in the point P. And of course, it's called cell-vertex because our variable, our unknown, is in the vertex of the element. So that you can construct the control volume in different ways. The element-based finite volume method is constructed. Let's say you have the grid here. Let's mix with triangular and this one. The unknowns are here. In the vertex of the element. Now you have to choose a way to create the control volume. In the element-based, what you do, you find the center of the element, the median, the center, median, center, and then you join. You join, and then keep going. Center, median, center of the element, median, and then center and median. Here's the control volume. Just created. You could do also in this way. I could join the centers with the center in a straight line. I could join in a straight line, a moment. Let's see if here the center, here the center, then I have this one, center with center, center with center. This is wrong. Center with center with center. Here is the center of all elements. And one way to do that, you don't have that. One way to do that is to join them by the straight lines. And the element-based, it does from the center to the midpoint of this side. It's center, midpoint. Center, midpoint. It's a little bit different. Center, midpoint. Midpoint. Of course, if you have a very, imagine if you have an orthogonal grid, it will be coincident, of course. But the element-based, the way we do here is center of the element, mid-size of the edge, center, mid-size. This is our control volume. And here is our unknown. And we are going to perform flux calculations and this in all these positions. So the construction of the control volume for the element-based is joining the center of the elements with midpoints. Let me just put here in order not to turn off all the moments. Here we are again. And there is the question I'm already explaining. How the elements participate in each control volume. For a quadrangular element, each sub-element or sub-control volume, if you want to call, they take part in the conservation for other control volumes. This part for this control volume, which is the node is here, this part for that and that part for that. So the element is split in parts which will feed up the fluxes for different control volumes. If it's triangular, of course, there will be three. We're going to see in a coming picture. Why we call element by element? Why we call element-based? Because everything must be calculated in the element. If you, let's say, if you are going to calculate this flux here, you cannot use this point or the other point. You have to use this one, because this flux is inside this element. That's why we call element-based, because everything is calculated inside the element. So to be an element-based, all calculations as fluxes, sources, and transient terms must be calculated using the properties located at the vertices of that element. If you use, let's say for this flux, as I was saying, using this node, this is not an element-based, because if you do an element-based, the structure is prone for efficient programming. The element-based sweeping, you sweep the domain in element by element basis. That's what is the nice thing of the methodology. It is clean for each element, and then we sweep the domain constructing your conservation equations. We are going to talk about that. What is the advantages of the element-based finite volume method? Well, I'm called element-based because the construction is this one. But of course, the control volume which arises joining by a straight line the center of the elements has the same analysis. The only difference that you may have some distorted elements, and your straight line is not going to cut in the middle of the edge. That's the difference only, you know. So it's suitable for complex geometry. Well, as any other method which uses unstructured grids. Allows the use of hybrid grids. You can join tetras, hexas, prisms, pyramids, and doing really complex geometry and satisfying some physical conditions, as I explained in the previous lesson about the boundary layer with these hexas and then tetras. Easy calculations of properties inside the element. Then you sweep element by element in order to construct your control volume equations. Increases the accuracy in large gradients. And that's what, in my opinion, is an elegant formulation. You know, it's clean, as I said. It's different from some numerical techniques which you know, it's difficult to program because the calculations does not follow the same structure all the time, so then makes it difficult to do some interesting programming. Let's compare. What is drawn here is a curvilinear grid. The conventional finite volume, you have the unknown here, and 4 integration points, balances, are calculated in those points. If it's an element-based, you use those and that and that and that element, you construct your control volume, you have 8 integration points compared to 4. If you are, let's say, evaluating a gradient, you have more integration points in the same distance. And then there is the stencil for the unknown and where you calculate the fluxes. And here is the conventional finite volume that you calculate in the middle of the face. So there's more integration points. That means an increased accuracy on the calculation. And this is a general picture, a general picture to recognize the entities which are involved in an element-based finite volume method. You have the grid. This is just a grid which is laid down on a petroleum reservoir. You have 3 wells and a geological fault here, some kind of barrier to the flow. It doesn't matter here. It just the grid was picked up from this problem. It's important to mention that there is a very fine grid resolution close to the wells. Here's the fault. From this grid, you identify, there is a zone there, so the grid's here. Then you identify elements, and one of the elements is here. This one is here, the element. And then you have the place where you have your unknowns. You have a subcontrol volume or sub-element. You have the integration points, which are in the surface. You are going to make the balance of your quantity. And then unknowns, integration points, and the blue color, control volume, gray, the elements, all the entities here. Elements are the basic geometrical entity for the discretization. The elements, they are the basic. The problem are the nodes, vertex of the element. The differential equations are integrated in the blue region, control volume. The fluxes that crosses the control volume surface, obviously, are calculated in the integration point, which lies in the middle of each region here of phase. So this is everything in 2D. It's easy to visualize, you know. And then what's happening here is the same as we have seen in curvilinear coordinate system. There is a local transformation now. Imagine you have an element here. You have every element has the number of integration points is the same as the number of nodes, of course. I have 1, 2, 3, 4 nodes, 1, 2, 3, 4 sub-elements, 1, 2, 3, 4 integration points. So what is done is a transformation for this region, which is the real region, and map it to a local transformed domain, which is where the eta and xi are the new coordinate system, and we have xi equal to -1, xi equal to +1, eta -1, eta +1. So the area of this transformed element is 4, 2 times 2, 4, and you have the area, which is the physical area here, which is related by the Jacobian, as we already visited studying curvilinear coordinate system. So there is a transformation. X is a function of x and xi and eta, y is a function of xi and eta, and you have the transformation, you have the inverse of the transformation, everything is the same. What you can do now, working with in the transformed domain, is to have to specify, to represent your coordinates x and y. See, I'm doing everything in 2D here in order to be easy, as I said. X and y, it's a summation of the shape functions and x in every point. Y is the same. For the y is the same. As I already mentioned, not in these previous 2 lectures, but in the other ones, shape functions are not merely, they are just merely some averaging of the values which I have in the nodes. And this is the shape functions we call bilinear. With 2D, bilinear shape function for the square. N1, N2, N3, N4. 1, 2, 3, and 4. And they are 1 over 4, 1 plus xi, 1 plus eta, N1. And it's easy to construct the shape functions because point 1 is in xi 1 and eta 1. So they are plus and plus here. N2 is eta 1, xi minus 1, so minus plus. It's easy to construct the shape functions. N3, minus minus. Xi minus 1 and eta minus 1. Minus minus. Eta 4, plus minus. Plus minus. So now if you want to have, let's say, I know these coordinates, right? X and Y here, I know this came from the grid generator. I know all the X and all the Y's in the vertex of the element. So if I want to have the X and the Y in the center of the element, which is right there, what you will do if you don't use shape functions, you will do some kind of average. But this is really the average too. In the center, xi is equal to 0 and eta is equal to 0. So you just put 0 everywhere here. There's the x in 0, 0 will be the average over the 4 vertex points, because 0, 0, 1, 4, 1, 4, 1, 4, 1, 4. So it's an average of the x and the y's in every position. So shape functions are not really a strange, let's say, let's say a new or something that should be give some special treatment. They are just merely the way to represent variables inside the domain based on the values on the vertex. Can be x, can be y, can be a function phi, any function. The next slide will show that. This is the transformation for a quadrangular element. The shape functions, I have 4 of them, n1, n2, n3, and n4. If it's a triangle, it's the same. If it's a triangle, it's the same. You have your triangular shape here, 3 vertex, 3 nodes. These are unknown, will be here and there and there. Of course, it is 3, it's divided in 3 sub-elements. There is 3 integration points. Every sub-element will take part in the balance of one equation. This one for the equation for the node 3, and this one for the equation and the node 2. And how it maps? This way. Xi and eta 0, 0 here, and here the axis, and this is the shape functions. I didn't mention the value of the shape function in the point where it is defined is equal to 1. And the other ones are 0 on that point. You know, let's say n1 in the point 1, 0, 0, n1 in the point 1 is 1. Of course, n2 and n3 has no influence on the value of this point, right? And then n2 has to be 0 when calculated here. n3 has to be 0 when calculated here. So at this point, eta and xi are 0. So n2 is 0, n3 is 0 here. It's obvious. So the other 2 points, they don't influence the value which is established for point 1. The same way, n3 has to be 1 in this point. What point is this one? Is eta equal to 1. And the other one is 0 there. This is the properties of the shape function, which is natural property, in order to take in account the influence, what it's doing. If you calculate it somewhere in the middle of the element, if you are calculating here, you have your transformation here, then you have some related point there. Then you just, no? You can calculate in the vertex, in the center, in any point of the element. So it's very nice you use the shape functions for that. As let's say closing remarks here is that all calculations are performed at element level according to the local coordinate system. So phi of x, xi and eta, phi, eta, shape functions, these are the entities. Here is our transformed quadrangular element in the xi eta coordinates. Then you can calculate there, for example. Point at the interior of the element. You choose the point where you want to calculate everything. You can calculate coordinates, functions, and gradient of a function. Everything with it. If you have the 4 shape functions defined, x and y, we already explained how it is. The value of phi here, by the way, is just to know what kind of xi is this one, what kind of eta is this one, and to calculate eta 1, eta 2, eta 3, and n1, n2, n3, n4 for this point. And these are the 4. So this is a summation in 4. So this the phi, let's say the phi and some xi and eta is n1 in that point xi and eta times phi. You know, the summation n1 times f1 plus n2 in that point times phi2 and so on. That's the way you calculate the phi in any interior point. Gradient of phi is the same. The gradient of phi is the same. Now you have to have the derivatives of that. And then derivatives, they are relate to the shape functions too, the derivatives. So you calculate value of the coordinates, you calculate the value of the function and gradients of the function on the point. Everything inside the element. And gradient calculation inside the element. What is a gradient? D phi dx I, d phi dy j. How I represent the derivatives of phi related to x using the shape functions. This way. It's the same. It's a summation in the 4 nodes. Derivative of the n's shape function related to x. And the derivative of phi related to y is the derivative of the shape functions related to y times the phi is the same summation there. But instead of having phi, if I have the derivative here, here's this derivative of n1, the derivative of n2, of course, is you find that directly. But now we need to use the coordinate transformation because the n's are not function of x. The n, they are function of xi and eta. Then what I have to do now is to find the derivative of n related to x in terms of the derivative of n related to xi and eta, because those derivatives I have, because the shape functions are not function of x and y, function of xi and eta. But I need the derivative related to x and y. But it's easy to do this transformation. You do this transformation. You apply the chain rule. Derivative of n in x, derivative of n in xi. Since x is a function of xi and eta, so the derivative, there is a small matrix here in 2D, and then you find derivative of n related to x and derivative of n related to y, everything as a function of numbers that I can calculate. Derivative of shape functions with eta, I know they are function of eta. Related to xi, I know they are function of xi. Those are the coordinate transformation. That's when I map a real x and y points in a global coordinate system, and I map it onto a 2x2 transformer domain. So this is easy to find. So I can put there, and I have the gradients of phi inside. See, there is no need for any kind of graduated reconstruction, Gauss, Green-Gauss theorem, and surrounding nodes, because it's clear that if I have let's say a triangular, I can have some phi which is a function of x and y and xi and eta, and if I am inside here and my integration points are here inside, I can find the gradient easily just using those 3 points. So there is no need for gradient reconstruction. You know, this is let's say the main difference between cell center and cell vertex. Cell center, you need a gradation reconstruction. Cell vertex, you calculate the grades directly using the vertices, the values on the vertices of the element, you know. Then this is the transformation. So those derivatives appears here. The x, dy the eta, dy the xi, they are here. They're the same. If y is related to the, it's not here at the moment, the previous slide. If y is the summation of n, the derivative of y is the derivative of n, it's summation. So everything is nice, clear, clean in order to compute all this. Before I go to the explanation of this, I would like to make some comments about this, what we call element-based finite volume method. This technology, this way to solve problems, fluid flow problems, using unstructured grids, the beginning of this work started with Baliga, Rabbi Baliga. He was a PhD student in Minnesota, supervised by Professor Patankar, and he started with using triangular meshes, unstructured triangular mesh for solving fluid flow problems. But he didn't use the shape functions at the beginning. He had a triangular element, and I can say that phi is some xc plus b eta plus c. Because if I have three nodes, a plane crosses. No, you can put a plane passing through the three nodes. And then he didn't use the shape functions. He was the derivative relate to x, to y, to xi. This, of course, there is phi in terms of x and y, and then you have the transformation. Everything is the same. But he didn't use the shape functions to represent one point inside domain. Instead, he used a linear function, because in 3 points you have a plane which is passing through. And then element-based was called by him in the beginning control volume finite element method. And then and still today in the literature, if you go there and you put EbFVM control volume finite element method, you will find a lot of reference on that. Control volume finite element method is the same as the element-based finite volume method. Why there is part of the community which calls element-based finite volume method, and I'm in favor of this denomination, because control volume finite element method conveys you to think that it's a finite element method which uses the control volume. Will there be a finite element method using the control volume, which is not true. It's not a finite element method, because finite element method, they don't have the concept of control volume. They don't have the concept control volume. They have only the element. And control volume finite element method looks like, it seems that it's a finite element method which uses the control volume, and it's not. It's a finite volume method which uses the element. It's a little bit opposite. It's a finite volume method which uses the element. So it's an element-based finite volume method. After Baliga came Michael Raw, who did his PhD thesis at the University of Waterloo, and he kept calling control volume finite element method. And then, literature spreads Sometimes it's control volume finite element method, sometimes it's element-based finite volume method, but it's the same. It is exactly the same. The only reason I'm put some historical, little historical point for you is that it seems, for me, element-based finite volume method is clear saying that it's a finite volume method based on the element. That's what it is. It's not an element, finite element, which uses the control volume. That's the main reason, just to give some historical point of view on that. Example of a shape function. Just a gente visualize the shape function. Let's get the N1 here shape function. The N1 in a quadrangular element, it looks like this gray drawing that we have here. So the value of N1 in the point 1 is 1, has to be. The value of N1 in point 2 is 0, because N1 in the point 2 is 0. N1 in the point 3 is also 0. We just talked about the N1 is 1 in the point 1. Of course, N1 has no influence in the point 3, has no influence in the point 2. So therefore, N in the point 4 again. N1 is 0 here, 0 here, 0 here, 1 there. And keeping let's see, at a constant xi, it's linear, of course. If I put one of these two terms constant, it's linear. It's linear with eta here. It's linear with xi there. 0, 0. Then you already know that maybe I said that in the past. It looks like you have a piece of paper or cloth or something like that, that you fix it at 1, you stretch 0 there, you stretch 0 there, and let it lay down, something like that. It's not a plane, it's not linear, there is some curvature. I try to draw the behavior of the function from point 1 to 3. It's like that. So it's a bilinear function. So it's a linear if for xi is constant, it's a linear for eta constant, but it's a bilinear function in the rest of the domain. 0, 0. This is the best way. Now, if you do the same drawing for N2, will be 1 there, 0, and N3. So when you calculate some point value of some variables inside the element, you are put the balance of each shape functions in that region. So that's the summation for in 4 in this case. This is the N1 shape functions. It's nice to see this picture because we keep in mind how is N1. N1 is this kind of surface, which is 0, 0, linear, linear, and some nonlinear behavior inside the element. Well, then we have other shape function. I'm going through that just with another nomenclature here. Instead of 1, 2, 3, 4, 0, 1, 2, 3. But it's the same, Xi and eta, they are here in the 0. 0, 0, 1, 1, 0. Then you create the shape functions. Depending on where you put your axis, they are different, of course, right? If I put my axis in the center, it's minus 1, 1. See that it changed how the shape functions looks like. But the geometry is the same. It's the square. but the one that we have shown before, the x and eta are in the center. And this one is here. But of course, n0 has to be 1 in this point. What point is this one? 0 and 0. 0 and 0, and 0 is 1. In this point, n0 has to be 0. So in this point, what point is this one? C is equal to 1, eta is equal to 0. So eta is equal to 0, n0 there, n0 is here. C is 1. 1 minus 1, 0. So n0 is 0 there, 0 there. So it's the same. But the function changes if you change the x and y axis inside your element. That's obvious, you know. It's okay? And then triangles, you have 3. This is showing how many, there you have 4 sub-elements or sub-control volume, 3. If you go for 3D, shape functions, you have the axis there in the 0. Xi and zeta and eta, and then the coordinate points are 0, 0, 0, 1, 0, 0, is there. 8 sub-control volumes, and here's the shape functions. You construct the shape function with the property of being 1 in the point of that shape function, and 0 in all other points. Then you construct with this property. It has to be 0 in all other points except at point where the shape function is being defined, which is 1. So this is the tetrahedral element. 4. Tetrahedral has 4 nodes, 4 vertex of the tetrahedral. So there is 4 sub-elements. And to build the function. So this is the way to build the function. I'm stressing this point. The way to write the shape functions is just with the property of being 1 and 0 all over of the rest of the points. So prism. So this is then 6 sub-elements. And then it's easy also to construct this pyramids. A pyramid, you have 5 nodes, 4 in the base of the pyramid and 1 in the top. So you have 5, 1, 2, 3, 4, 5 sub-control volumes. So every part of this element will take part in the balance for the node which is here. The other elements contribute to the other parts. Here is the shape function. Here the shape function. So the element-based finite volume method, now thinking about how do you write your program, how do you construct your program. What you do is to create matrices. Let's see here. All you does that, you divide in 4, because you have one unknown here, another one there, another one there, another one there. 1, 2, 3, 4 integration points. What I want to do is to stop in this element, and there is one flux here. For each. What I want to do is to calculate this flux as a function of nodes. And then I do all the calculations. I calculate this one, this one, this one, this one, and I save this in a matrix 4 by 4. And I save this in a matrix 4 by 4. A matrix A with the 4 nodes, and I'm calculating the flux on that. And I save, what I'm saving in this matrix, 4 fluxes. When I'm going to build the equation for this control volume, I will use this one and this one. But they are there in this matrix, which I saved this matrix. And then I'm just going to, in order to construct the approximate equation for this control volume, which here, I exaggerated here, with the center here, I need this one. I need the other one that, well, that comes from the other elements. This element, I calculate these 4 fluxes and I save in a 4 by 4 matrix. If it's triangular, it's a 3 by 3 matrix I'm gonna save. And then I just will sum up for some control volume. Let's see this one. We have 7 nodes, 3 elements. 7 nodes and 3 elements. And because it's local, there is one pattern that I will say 1, 2, 3, 4. So the element 1 is the nodes 6, 3, 2, and 5. Remember that the numbering of the nodes is based on a global, because these numbers means 10,000 or 1,000,000 nodes that you have in the solution. Every element is connected to some numbers. In this case, it's 1, 2, 4, 5 for the element 2, 5, 6, 7. It could be, this number could be 11,000, that one 20,000. So the element there has the 4 nodes. This is the connection. There is the connecting structure, the data structure. But it's always like that. 1, 2, 3, 4. When I see locally, it's 1, 2, 3, 4. 1, 2, 3, 4. Say 1, 2, 3, 4. 6, 3, 2, 5. 6, 3, 2, 5. 1, 2, 3, 4. 4, 5, 2, 1. 4, 5, 2, 1. 1, 2, 3, 4. 7, 6, 5, 4. So this is the mixture of the connecting. So the connectivity is related like that. And then you go in this element, you calculate the flux here, and then when you want to do the control volume, let's say 5, the contribution of all neighboring elements. So you save, like is explained here. I have 3 elements there, right? Then when I sweep by elements, I will create 3 matrix. They are all 4 by 4. This is 4, this is 4, this is 4. They are all 4 by 4. So I have 3 local matrix. Now I'm going to build, let's say, the equation, the conservation equation for the control volume 5. This one uses this part of the element, this part, and this part for this control volume. Here's the matrix, the final, and see how it's a 7 by 7. Your final matrix, your global matrix, 7 by 7, because I have 7 variables, 7 unknowns here. So it's 7 by 7. But in this matrix with the conservation equation, the entries come from that matrix. So I have to use for this one, this and these fluxes. So involves the point 6, 3, and 2. 6, 3 and 2, and the 0.5. Keep an eye on the yellow element which contributes to the control volume centered at 5. This flux has to enter, and this flux has to enter. What are the global points which enters? 6, because in order to calculate this one, this matrix is already connect this flux with 6, 3, and 2, and this one too, with 6, 3, and 2. And the 0.5 enters, of course, and then is 6, 3, and 2, and 5. Of course, here is also 2, 3, 5, and 6. How does the element 2 contribute? With this flux and this flux. What are the points with the enters? When I'm calculating this flux, which is in this matrix, I'm going to use 4, 1, 2, and 3. 4, 1, and 2. 4, 1, and 2, and of course the 0.5. Here, 1, 2, 4, and the 0.5. Then I'm adding, and this is the final. This is the final matrix. You just add in the entries to obtain your final matrix. And this part of this entries comes from the local matrix that you have. I have another example which is the same, but just having now some, there's a triangular element also here. Now it's 1, 2, 3, 4, 5. 5 elements. There is 2, they are triangles. So there is this matrix for the element 1 is 3 by 3. And this one is a 3 by 3 also. Well, there's another one here. The 3 is 3 by 3. And this is the 5. It's 3 by 3 again. So there is 2 square and 3 triangles. So are these matrices? So you put then is the final matrix. Here's the control volume is for the node 4. Then you see, I have to use this flux and this flux. What for the 4? I need the 0.2, the 0.3, and 0.6. The matrix. This is the element 4. This is not very well clear, the picture. The element 4. The element 4. Element 4, which contributes to the grid point unknown 4. They use 2, 3, and 6, and the number 4. 2, 3, 6, and the number 4. So you build the matrix this way. You know. In order to see now how you build, let's see for the tetra. Here's the tetrahedral element 3D, of course, with 4 subcontrol volumes, 4 subcontrol volumes, blue, red, yellow, and green. Then here there's some exploded. The element green, the sub-element or subcontrol volume green. Unknowns are here. You can see that when they connect there is integration points. But they're there, and the other one is behind. This is the element, the sub-element in a tetrahedral element. And it does like that. In order to create a control volume, I need 8 tetrahedrons there. To see this is the tetra. The blue sub-element, the green, the red, and the yellow. Now, and the 4 nodes in the 3-dimensional. Now you extract the sub-element. There is 3 integration points here. It's going to So there are the 3 integration points on that sub-element. This will enter, here you have to calculate the fluxes. It goes to the conservation equation. So this is part of that element. So now I want to have the control volume for this point. I need to have the sub-elements for the others. So I need 8 tetrahedrons to do the control volume for this point. It's going to disappear, you know, there. So this 8 tetras here. Now let's explode it, and this is the control volume. So this every contribution 3 integration points. The other contribution, the other element 3 integration points. So it's 3 times 4, 12, 24. It's like, yeah, it's 3 and 3 and 3 and 3, 12 and 12 in the lower part. So I have 8. There is some flying triangles, tetras here, but this is the control volume, the 3-dimensional control volume, which results in the construction using tetras in 3D situation. You know, then we can see a little bit more clearly how you can, in order for using tetrahedrons, in order to build the control volume, you have to put 8 tetrahedrons together, and one part of each one generates the control volume. Where I am now, here. This was an animation made by Ricardo Rezende, when he was doing his master, he did this animation. Let's talk about hybrid grids, how powerful it is to use hybrid grids. And this is, the example here is a petroleum reservoir simulation, which has a geological fault here. There is wells there, 3-dimensional, everything is tetra here, everything is tetra in the main reservoir. But there is the well there inside the reservoir. The well is the line, and then around the well you have like a polar coordinate system. And this polar coordinate system, they are axes. And the geological fault has some dimension. And then in geological fault, you have tetras. Let's say it's like that. So you have tetras. Axes. And then you have to combine pyramids with, in order to represent axes around the well, and then axes in the geological fault, everything connecting with tetras as the main discretization being tetrahedrons. You know, another example, also related with petroleum reservoir. But in this case, with another application, is an application where you have a Cartesian grid. To solve the Cartesian grid, there is the reservoir. Normally the most used reservoir simulation, the flow in the reservoir, we call petroleum reservoir simulation, they use what they call the corner point grids, which are general Cartesian grids. Here are these Cartesian grids, and then you have a well. And if you imagine in a reservoir, when you use the dimension of the reservoir, you have grids which are 10 by 10 meters. And then in this grid runs a well, which is 10, 15 inches. So it's a line in this big, large grid of the reservoir. So it's not easy to solve with details the flow around the well, because if you have a grid which is 50 by 50 or 30 by 30 or something like that, how you can calculate the flow close to the well precisely? Then you have to refine close to the well. But if you are going to refine close to the well, refine the Cartesian grid, imagine the size of the problem. Because if you refine, then you will refine all the reservoirs, so the grid will be extremely refined if you try to refine it in terms of the Cartesian. And you end up with that problem because the well does not fit with the Cartesian grids. And then what is possible to do is to extract some control volumes which are Cartesian and put it in this hole that you made extracting Cartesian grids. You put an unstructured grid. And an unstructured grid which follows what we saw before. Axis, which is like a polar grid around the well, and then transitions from axis to tetras using prisms, and then it will be something like that. The white part will be extracting the Cartesian grids. The yellow line is the well. And then this dot line here, you are going to create this grid around the well. So, and then you put pyramids on the top of this blue, because this is hexa, right? A pyramid fits there, square based fits. We can see clearly here is pyramid there. And then comes the tetras. And then you have now you can have the full reservoir with what we call the near well region, discretized using hybrid grids, which is you can do this grid very fine here. Then you are able to calculate the velocities of oil, water, and gas entering the well precisely, because you have a refined grid. And then after you leave, you are far away from the well, then you have the transition, then you go to tetras, and then the tetras connect to the Cartesian there. And then you solve the problem, and then you have the chance to have a very good solution for the near well region, which is not easy to do. Doing some refine of the Cartesian grids, you know. So this is done. After that, we use the element-based finite volume to construct the two-phase flow in the well, you know. So these are the geometrical aspects of the element-based finite volume. So you have a transformation, you have grids, you have the possibility of using hybrid grids. What you have to do now is to integrate our equation.